Next topic is MCG, or we can say it is moving coil galvanometer. We have already discussed that torque is M cross B, and in terms of magnitude we can write it torque equal to MB sine theta. Here this M, this is the magnetic moment, it can be written as NIA if N is the number of turns, I is the current in the loop, and A is the area of cross section of the loops. Then magnetic moment will be M equal to NIA. We can replace this, so we will have NIAB sine theta. This is the torque on a coil in a magnetic field B. If this magnetic field B is radial, in that case this theta will be always pi by 2, or we can write torque will be equal to NIAB. This will be the maximum torque on the coil. Now, because of this torque, the coil rotates in the magnetic field, and in moving coil galvanometer, a spring arrangement is used which opposes this rotation, and an equilibrium is obtained. Torque is counterbalanced by the restoring torque. So this torque tau is balanced by a restoring torque where k is a constant and phi is the suppose angle rotated by the coil. Therefore, we can write it is NIAB, that is equal to k phi. So phi is the rotation made by the coil. Therefore, phi is equal to NIAB by k. Here we define two parameters. One is current sensitivity. It is defined as the rotation or angle of rotation per unit current, and it is defined as phi by I, and it will be equal to NAB by k. Here N is the number of turns in the coil, A is the area of cross section of the coil, B is the magnetic field, and K is a constant of the spring. Here this sensitivity can be increased if V increases the N. If N is increased, then phi by I also increases. Suppose V makes N dash equal to 2N, then this implies that phi by I dash will becomes 2N into AB by K, or we can write it is 2 into phi by I. So we say if number of turns are increased double, then current sensitivity of the moving coil galvanometer increases twice. Similarly, another is voltage sensitivity. Number 2, voltage sensitivity. It is defined as deflection per unit volt or per unit potential difference applied. Here we have written that phi by I equal to NAB by K. This is the current sensitivity. If we multiply this with R, so this is NAB by K into R. This IR is the voltage, so we can write phi by V equal to NAB by K into R. So we can write voltage sensitivity is NAB by K into R. Here, if N is increased, then R also increases. So this implies that phi by V, that is the voltage sensitivity, remains unchanged. It means increasing the number of turns, current sensitivity increases, but voltage sensitivity remains unchanged, because as N increases to say twice, N dash equal to 2N, then R dash also becomes 2R, and hence phi by V, that is the voltage sensitivity, remains constant. The galvanometer can be used to detect the current in the circuit and can be modified to measure the current and the potential difference. For this purpose, galvanometer can be converted to ammeter. This is A for ammeter, and this ammeter is used to measure the current, and this ammeter ideally has 0 ohm resistance, and it is connected in series in the circuit, and it measures current. While if galvanometer is converted into the voltmeter, then ideally resistance of the voltmeter should be infinite, that means very large, and it is connected in parallel and it measures potential difference across 2 points. Conversion of galvanometer in an ammeter. For this, a low resistance shunt wire is used in parallel of the galvanometer, and this whole circuit is commonly called ammeter. This is the ammeter. Here in this circuit current, suppose we have to measure I. This is the maximum current which we have to find, that is called the range of the ammeter. To measure this I, we choose the shunt resistance as in such a way that the current Ig is flowing through the galvanometer. This Ig is the galvanometer current which give full scale deflection in the galvanometer. Then remaining current I minus Ig will flow through the S, and because this point A and B are at the common terminals of for S and G is the resistance of the galvanometer, S is the shunt resistance, we can write that Ig into G, this is the current in the galvanometer multiplied by the resistance of the galvanometer, must equal to current in the shunt resistance I minus Ig into shunt resistance. This is the condition to get the ammeter of the particular range. Here I is the maximum current, or we can say it is the range of ammeter, where Ig is the galvanometer current which give full scale deflection in galvanometer. G is galvanometer resistance and S is shunt resistance, and shunt resistance is always a very low resistance which is connected in parallel to the galvanometer to convert the galvanometer in an ammeter. Similarly, we can convert galvanometer into a voltmeter. Conversion of a galvanometer in a voltmeter. For this purpose, a high resistance is connected in series with the galvanometer, say this is S, and this combination is called the voltmeter. And this voltmeter is connected in parallel across the terminals for which we have to find the potential difference. This is the resistance R across which this voltmeter reads the voltage. For this, if V is the voltage, maximum voltage which we have to find, that is, it is the range of voltmeter. And for this particular voltage, the current in the galvanometer should be Ig. This Ig will give the full scale deflection in the galvanometer. So we can write that V equal to Ig into G plus S, where G is the resistance of the galvanometer and S is the high resistance connected in the series with galvanometer. So this is the equation which is used to convert the galvanometer to a voltmeter of the range V. And for this V, this Ig is the current which gives the full scale deflection in the galvanometer. So using these two equations, we can convert the galvanometer in the ammeter and the voltmeter.